Hello Calc. We are looking at this video after we've finished working on volumes by washers, discs, and shells. So this video we'll be doing another kind of volume, and I'm not sure what date you'll be watching it because I'm not sure how long it's going to take you to do the problem sets, but I'm aiming say at the 20th, so we'll try that. Sorry for the dramatic pause. Okay, so what we're looking at this time is volumes of solids with known cross sections. Alright, that's a mouthful, and I'll teach it by example. So let me write out a problem for you. The base of a solid is the region enclosed by y equals square root of 25 minus x squared. Hopefully you can recognize what kind of figure that is. And the x-axis. Cross-sections perpendicular to the x-axis are squares. Okay, so if you were to think about this function and you didn't recognize it right away, you could fool with it, square both sides, move x squared to the other side, and now you should recognize that is a circle with the center at the origin of radius 5. Alright, so knowing that, now let's go ahead. We are going to look at the base of the solid. The base of this is the region enclosed by this, so let me get that. So this is where my sketching is sketchy. So suppose we have a circle, radius 5, and it's center at the origin, but we're looking at the area that is enclosed by that and the x-axis. Alright, so when it has a plus out here, we're assuming this part. So that's what we're looking at. We're looking at that area. And it says that cross sections of this solid perpendicular to the x-axis are squares. So I'm going to try to draw it this way and then another way. So here is a cross section and it's perpendicular to the x-axis, and that is the side of the square. So where's the rest of the square? Well, it's going to be rising out of the paper straight towards you, so I should draw it like this. But I'm going to try to draw it with some sort of perspective. I don't know if that looks like a square. All four sides are supposed to be alike. It's probably a little too tall. Alright, then the next cross section is going to be, this is the side of the square, but it's going to rise up towards you. If it was, I draw it exactly, it would come up out of the paper like that. So, but I'm stuck in 2 dimensions with my paper and pencil. And now I'm going to draw a couple more. And notice there's going to be one down here when it's near the end point. It's going to be very small. And over here there's going to be a tiny one rising up. And so forth. So imagine coming across this figure with cross sections that are square all the way from here to here. So what kind of figure will we have when we're done? Well, it's going to look something like that, where this was supposed to connect all of these. So, not like I said, I told you my sketches are going to be compromised here with my talent. Alright, compromised by my talent. So, we have a figure that has 3D shape. It has like a surface that's going like this, that's real thin, widens out, and then it gets real thin again. And the side, I don't know, it's very hard to picture this, but it's going to come out of the ground like this. And if I was trying to draw it by itself without any graphs, would kind of look like this. That's still not very convincing. So one of the squares would look like that. Now, I don't know how to draw it, but anyway. Alright, we're going to go ahead then and do the calculus, and it turns out that it's not too bad because in theory we're going to have all these squares, and one of the squares, I'll draw this side view. Here's the side of one of the squares. It has a thickness, it has a side and another side. So its volume of just one of those thin wafers, square wafers, is s squared, and then a very tiny thickness. And the thickness of one of these is right here, and it's red on the x-axis, so I'll call it dx. Alright, so we're going to take, in this case, we're going to take the volume of the square, which is s squared dx, and we're going to add them all up. And we're going to stack these up between negative 5 and 5, although I can see this as a very symmetrical figure. When I do that, I like to start with 0 and go to 5 and then just double it. So if you're pretty sure your object is symmetrical on one side of the y-axis to the other, that's a good trick to employ. It cuts down on the integration mess. So, alright, so we can't work with s's. We have to think of what this value is. So looking at this picture, let me pick one square. How about this one? Try to darken it. Alright, that's one of the squares. The one I'm going to help me get the value in here. So I can see that the side of the square, actually I shouldn't have drawn it like that. It doesn't go to the origin. It could, but I meant one like this. So you can see my perspective is off. So here's the side that's perpendicular to the x-axis, and here's the rest of it. So that's supposed to be a square. Alright, so one of the squares making up all of these squares is right there. And notice the side. It is perpendicular, supposed to be, to the x-axis, and it starts here and it ends here right on our function. So if I went over x and up y to get to this point, you can see that this value isn't s squared, it's y squared. It's the y value of our function. However, since we're in dx land, we have to work in x. So I'm going to have to rearrange this. So, well actually it's already rearranged up here. Up here in the beginning, we see y equals the square root of 225 minus x squared. So we'll go ahead and pop that in there. square it. That's nice. Alright, so then we end up with a integral that's quite doable, because the square root squared just leaves me 25 minus x squared dx. And I always ask you to do one by hand, so on this assignment I would pick this one. 25x minus x cubed over 3, a 0, and a 5. So I end up with 25 times 5, which is 125 minus 125 over 3. And all that is still multiplied by 2. So when I did all that, I got 500 over 3. Alright, so I did the fraction work multiplied by 2, and I got 500 over 3, and that's units cubed, because it is a volume. So our structure, probably the best picture is right here, has this as its volume. Alright, I'll do one more so you can get the gist of these even better. So I'll do that on part 2. Till we meet again.